First, I want to say thank you to everyone for joining us here. I'm just going to move my picture a moment. I want to thank everyone for taking the time to be here with us. This is actually the first time I've given a webinar, so it's a new kind of venue and platform for me. So thank you for going on this journey with me. I think that actually today what we're kind of all experiencing is really unprecedented and remarkable times. And so as we kind of come through this and as we come out of this, we're going to be needing to look at every potential opportunity that presents itself. And so I thought that when Cheatham asked me to give a talk, I thought that doing a review on something like ruby treatments might be a good opportunity and a good thing to kind of cover. As the title kind of indicates, ruby is really kind of king of the colored gemstones. I think it's the market leader for colored stones throughout our industry. So I just thought it was a good, timely moment to maybe do a review. Okay, so we'll start with talking about commercially available rubies that are in the marketplace. And here we essentially have three different types of rubies. So we've got unheated rubies, we have heated rubies, and we have composite ruby. And so this is what we're going to cover through the course of this discussion. And there are different iterations of each one, things that we have to consider when it comes to treatments and when we're looking at them. And so this is what, by the end of this, all of this will hopefully be a bit more familiar for you. So when we look at rubies that are available in the marketplace, you have stones such as these. Any one of these stones could come across your desk or come into your office at any time. And you really have to know what are the questions to ask when you're looking at them, because you want to be able to properly identify them. And so this is an important aspect to kind of consider. And so this is what we're going to cover, because all of these stones, it's awareness really, which are considered to be your first line of defense. Awareness for the potential risks that you may be exposed to, as well as potential opportunities. And so with needing to be able to optimize every situation as we come out of this, this role or this aspect of awareness is really a key consideration. So when we talk about natural rubies, I think all of us, we like to envision stones like these, really high quality, untreated rubies, such as you have from Burma, from Mozambique, from Tajikistan, Kenya, Tanzania, Madagascar, Thailand. So many different locations around the world can really have the potential to produce high quality, beautiful gems. And when we think of rubies, this is really what we kind of visualize in our mind. Gems such as this. This is what spurs the creativity, the imagination when talking about stones or jewelry, for within the trade, for jewelers, but also for consumers. But to produce a stone like that, you need rough like this. So this was a very high quality piece of rough from Burma. And you need stones which have this intrinsic quality which nature had bestowed upon them. It's only through these that you're able to really kind of end up with stones like we just demonstrated. But stones such as this are really by far the minority of what is recovered. The vast majority of rough which is recovered from the different mines around the world is more rough like this. This is industrial grade material. This is material that's not even transparent, it's translucent to opaque. The colors are off. And so this is by far the bulk of what every mine is producing, this kind of material. And so this is why there's an appreciation evaluation also for high quality untreated gemstones. But it's no wonder that since the earliest kind of treatise on gems, we find commentary about methods that were used to try and improve the appearance and improve the quality of gemstones. It's because untreated rubies and sapphires were so rare. So we see this from very early on. So where are we going to start? We'll start with unheated rubies, and a little bit of this question of how do we determine that a ruby is unheated actually. This is something that as we talk a little bit more, we're going to find out this is much more challenging in the strict sense than most people kind of realize. But I'm going to kind of bring people through a certain part of this discussion. The thing I want to start with is this kind of classic symbol of what we all learned when we were gemologists, kind of starting and entering the industry. And this is unaltered rutile silk. we were all kind of taught that this was the sign of a stone that's unheated. But I really want to dispel a myth, because this is a fallacy. We know much better now that fine needles of rutile, they only begin dissolving at temperatures of about 1300 degrees centigrade. This isn't a fixed point. There are a lot of factors which will influence when rutile, actually begins the process of dissolution in stones, but it's plus minus around 1300 degrees. And so while unaltered rutile silk may be evidence, and is evidence that a stone has been heated above this threshold, it's not a confirmation that a stone is unheated, because a lot can be achieved in terms of especially color manipulation at temperatures well below this. So what are the kind of things that we need to look at? This is, the stones themselves have to be what is telling us. They have to give us the information that we're able to interpret. So we're going to look at things, something like carbonate crystals, calcite crystals, pristine, transparent calcite crystals like you see here and like you see here. These are mineral inclusions which alter even at relatively low temperatures. You're going to see signs of alteration. So inclusions such as this they provide more information about whether a stone has been heated or not. You have other minerals like apatite. Apatite is a little bit more thermally resistant than calcite, but these also will tend to alter at relatively low temperatures. You have things like micas, you have things like iron sulfide minerals like you see here. So when you see these kinds of inclusions that show no signs of alteration, you have much more evidence that the stone is indeed unheated or natural color. One of the things that people in the industry, your appraisers, gemologists, and people in the trade need to get more familiar with a little bit is looking a little bit more closely at stones, because you have to start to get familiar with what the inclusions you're looking at actually are. So the identity of these minerals, because the different minerals are going to alter at different temperatures. And so in order to really be able to interpret what you're seeing, it's not just important to see an unaltered crystal. You have to try and ascertain the identity of this mineral. So the idea of getting familiar with how to recognize calcite, how to recognize mica, how to recognize apatite, these things, how to recognize zircons, these things are going to have increasingly importance as time kind of goes on. We also use things like spectroscopy. So infrared spectroscopy, this was something that I discovered in the early 90s, was that actually we could identify foreign minerals occurring inside corundum through mid-infrared spectroscopy. So here, for example, is an inclusion of diaspore, and diaspore is an aluminum hydroxide mineral. You have others like boehmite, you have weathering minerals like kaolinite, goethite, gibbsite, and so on, that you can identify with mid-infrared spectroscopy. And these can help provide additional information because they alter, even at relatively lower temperatures. The presence of minerals such as this can help you ascertain that a stone is indeed unheated. There are also structurally bonded OH groups. Now, structurally bonded OH groups are something that can occur naturally in a corundum in ruby. They can also be induced or altered as a result of heating. So one which is sensitive that we're able to track is what are called the 3161 series. So it's a group of bands that always seem to occur together with the main peak positioned at 3161. This is also thermally sensitive. So if you start to see features such as this, you start to get an idea that a stone is not heated. So let's say you have a ring. Yes.
I have a question here, so you asked me to interrupt you. Before you move on any further, one of our attendees, David Atlas, is asking what kind of magnification is required for these inclusions. So can you actually clarify that before you move on to other inclusion photos?
Sure. So its magnification obviously depends on how large the inclusions are themselves. The larger the inclusion, you can get away with a loop. Many times a microscope is obviously better because you're able to change the magnification to what is needed. But many times it's the habit that you want to be looking at. So there are particular kinds of habits that you see, typical kinds of formations that you'll see for these minerals that help you to recognize them. You know, you have the photo atlas, which was done by Dr. Gublin and John Cuevela. This has a fantastic library of inclusions that people can just kind of flip through to get used to what these typical forms are. Micas typically tend to be platy and brown. You know, you have neobite, which tends to be, or columbite series minerals, which tend to be black and cubic, uraninites. So certain ones have certain habits. Apatites tend to be columnar and hexagonal. Calcites, you commonly see actually cleavage planes, which are present in the calcite crystals, but it really is dependent on the stone itself. But obviously a microscope tends to be the best tool to be able to use. I hope that helps to answer the question. So again, here we have a stone or a ring with a stone that we've been able to determine, let's say, or in our opinion, it's an unheated stone. But does the story really end here? This is where I want to bring in the topic of additional enhancements that you may encounter. Because just because a stone may not be heated doesn't mean that it couldn't potentially be treated in another method by another method or means. And so here, what we're most commonly talking about is actually the oiling of fissures. So I'm just going to move this to the side here for a moment. So the oiling of fissures in unheated rubies is something that most of the trade is not familiar or as aware of how commonly this is actually employed. And so just like when you treat an emerald, you reduce the visibility of the fissure by introducing a foreign material such as an oil. And in this particular one, I'm presuming you can all see the cursor. Here you see the iridescence kind of going diagonally through the middle of the stone. This is coming off of that fissure. But this whole picture is actually one large filled fissure. The visibility is reduced very effectively by the fact that there's an oil in it. From another direction, let's see here. As I go to another direction of taking the image in this stone, you can see where the fissure actually reaches the surface of the stone. You see this area over here to the left. This stands out in higher relief because this is an area where the filling was either incomplete or the oil has partially been removed. And this is what the fissure would look like if it was not oiled. You can see on the right-hand side, you also start to see a little bit of the iridescence. All of this image to the north that's extending over to the right is a fissure that's filled. You're looking through a filled fissure. And so this is something which is, as I said, more common than people realize. And when I've spoken about this before, I use this particular stone as an example because this is an actual stone that came into the laboratory by a client. This was a 5-carat stone. I called the client with results. I was able to tell them that it was an unheated stone. It was actually from Burma. And so he was very happy to hear this information. It was about 5 carats. And then, though, I had to follow up and explain to him that the stone was oiled. And because he wasn't familiar with it, he didn't quite understand. He thought this was something that just had to apply to emeralds. But it's so we had this discussion. I explained to him that it's something we have to disclose properly for full disclosure. And so we decided, settled, he said it needs to be removed. He doesn't want the oil in the fissures. So together we decided to remove it. I placed the stone in acetone, asked him to come back a couple of days later. And this is what the stone looked like when we pulled it out of the acetone. And so I think you can all probably imagine the reaction of this dealer. He purchased a 5-carat unheated Burma ruby that looked like this. And he realized he had an unheated Burma ruby that when you took out the oil, this is what it looked like. And so this even surprised me. I was not expecting it, but it really is a stark reminder that oiling can be very efficient at reducing the visibility of fissures, not just in emeralds, but also in rubies. So even if you determine that a stone is unheated, a ruby is unheated, you should take that time, take the moment to look and make sure that the stone has not been oiled. So next we're going to talk about the heat treatment in ruby, and I purposefully chose an image that has some antique jewelry with rubies in it, because we're going to want to talk about when did this process of heating rubies start. We're going to talk a little bit about how it's determined and answer a kind of fundamental question of, is this just a straightforward black and white kind of a determination or not? And so when we look kind of historically speaking, we look at this, I think it was actually Cheatham that sent me this excerpt. This is something that was published or written in 1240 AD. So there are written records which go back almost 1,000 years now of treatment heating that was done to rubies. Now here it was being done to remove black spots, which were actually probably just dark blue color zones. When we're talking about this heating in antiquity, we're always talking about relatively low temperature heating in the context of today. But just because you might be shown or have a stone that has a history, let's say it's 50 years old, or 100, a known history, 50 years, 100 years, even 200 years, it's certainly it's unlikely or would not have been heated at the more modern, relatively higher temperatures. But you cannot presume or just assume that the stone is unheated. You still have the potential for relatively low temperature heating. And so here I want to come to a certain context that also I want the industry to start to understand. And these are two specific statements that in general, it's easier to establish conclusively when a ruby has been heated. And this is because when you see the evidence, you're able to make a definitive statement that yes, the stone is heated. On the contrary, establishing conclusively that a ruby has not been heated, so meaning that it's all natural color, this can be much more challenging. And this is why you have the wording on gemological reports that you do. So when a stone is heated, you'll see a definitive statement, treatment or enhancement, heat. On the contrary side, you'll see wording such as no indications of heating or no gemological evidence of heating. And this is this wording was purposefully chosen because there is a certain limitation. We're looking at stones to try and see what that stone is telling us. And so there may or may not be enough information to determine conclusively whether the stone is indeed completely unheated or whether it's just a stone that has no indications of heating or no gemological evidence of heating. And so this is a context which the industry needs to also get more familiar with.
Hi, Chris. I have one more question. You go a little further. This is from Antoinette Matlins. While heating has been used for millennia, when was routine heating of virtually all sapphires begun?
So I'll talk a little bit more about that. In the beginning, we started to see this, really transitioning and becoming more common in the 70s and the 80s. So it is a more modern, kind of situation that we have. And I'll talk about that in just a moment, a little bit more. Oops. So here, this is an image that so let me go back to here again. When we talk about conclusively being able to recognize the presence or the stone that has been heated, but recognizing the fact that a stone is unheated can be more challenging. And this next slide illustrates this really quite well, because the inclusion you see on the right, when you see an inclusion like this, you see clear evidence, clear confirmation that the stone has been heat treated, so you're able to make a definitive statement. But what I want to do is I want to draw your attention over here to this mineral grain, because this mineral grain doesn't show any evidence of heating. Now, it just so happens the inclusion on the right was an apatite, the inclusion on the upper left was a zircon. So at the temperatures which this stone was heated, it was not sufficient enough to start altering the zircon. So if you did not have, in this stone, you did not have this inclusion and all you had were zircon crystals, it would be understandable if you don't have other evidence to confirm that it had been heated, that you might see a conclusion of no indications of heating or no gemological evidence of heating, but it's actually not proof. We have to go by the evidence which the stone itself is able to give us. And so here I'm also just demonstrating this is a stone that I had heated to 1100 degrees. So again, here you can see the rutile silk, it's very fine, it's all completely intact. I was heating it at a threshold below that to dissolve rutile silk. And so this is now another context which I want people to start thinking about. I've been speaking about it for more than 10 years now, and that's really, you have two essential temperature ranges when you're talking about heating corundum. You have relatively higher temperatures and you have relatively lower temperature heating. And the threshold in between this I use is that threshold necessary to dissolve rutile silk. So again, this is not a fixed point, this is not a fixed temperature because there are different variables which will impact when rutile begins to dissolve. But because we in the industry and we as gemologists, we were all taught to look for rutile silk in corundum. We all know what the appearance is. We're all very familiar with it. We know how to look for it. We know how to recognize it. And so it's a very good benchmark to use. Like I said, I've been talking about this for more than 10 years now. You start to see other organizations today also starting to use this kind of guideline for the threshold between relatively higher temperature and relatively lower temperature, because it's a good, practical, pragmatic application. So, but these are not official designations. This is just practical. So when we talk about relatively low temperature heating, we're talking about heating with a fire. We're talking about blowpipe. This is something that's been used for a very long time to alter or to treat corundum. And when we talk about relatively low temperature heating, we're really talking about color manipulation. And so relatively low temperature heating, especially when we're talking about rubies, is very efficient and very effective at breaking the charge transfer between iron and titanium, which produces the blue color in corundum. So you can have a purple sapphire change into a ruby. You can have a purple sapphire change into a pink sapphire. You can reduce or eliminate a purplish component which is present in stones, and this can all very, very effectively be accomplished at relatively lower temperatures. So when I come back to this, so as AGL is a laboratory, we've been disclosing relatively low temperature heating for more than 10 years now. As I've kind of indicated, I think AGL was the first lab to really start specifically disclosing relatively low temperatures, but you need to look for other things. This is why, recognizing relatively low temperature heating takes experience in looking for this in particular. And so I want to point this out to people. Some of the things that you can look for, like look at healed fissures. You have negative crystals and communication tubes present in healed fissures that sometimes contain CO2-rich fluids. And as you elevate the temperature, the CO2 gas expands, and it'll actually cause low relief secondary fissures, kind of like what you see here, extending off the healed fissures. This is a good sign that this stone is experiencing relatively low temperature heating. Here, as you see, there's an unaltered rutile silk, which is still present, but we have features such as this can start to give you an idea. When we talk about mineral inclusions that are more thermally sensitive, I use here apatite inclusions, calcite, micas, things like pyrrhotite and so on. This inclusion scene that you see is a Madagascar purple sapphire or color change sapphire. It's populated with a bunch of mineral grains like most of you should be familiar with in Madagascar stones. And at relatively low temperature heating, you can see from the background, the color was very, very effectively changed. And here we had a crystal of apatite, which a discoid or atoll type of stress fracture took place surrounding this stone. But if you also look, the whole area, let me try to point to the camera. So the whole area, you see a lot of mineral grains which were zircons, and these were not affected at the temperatures of which this stone was heated. So it's also a reminder that you have to really take your time to look at stones and look at all of the inclusion features and what they may tell you. Don't just take a quick look, you see a bunch of what appear to be unaltered inclusions and just stop there. You really want to investigate a little bit further and try to recognize what kind of minerals you're dealing with and what is the condition of all of the inclusion features that are present. So a very practical guide, just most of us have UV lamps. Shortwave UV fluorescence is a kind of simple, quick method that you can do. Not all stones show this kind of blue-white chalky fluorescence, but when it does, it's a good indication that a stone was heated. So it's something that most gemologists have available to them. When we start to talk about infrared spectroscopy, this was a Mongsu ruby. It had inclusions of diaspore, which we were able to recognize. Again, I showed this and published this in 1995. We're seeing that even relatively low temperature heating, what happens is the diaspore goes through a process of dehydroxylation. already at about 450 degrees centigrade. And so you convert the aluminum hydroxide into aluminum oxide, and the hydrogen is then diffusing into the lattice where it's creating structurally bonded OH groups. So you can see this transition take place in the infrared spectrum. And so even though you might have inclusions that may not give you a clear guidance of whether or not the Monkshoe ruby has been heated, something like infrared can help you very much. There are other types of structurally bonded OH that we're able to track. These are really minute. This kind of comes into a little bit more of criterion, which was not widely published until recently. I said, I've been doing this for a long time. This was criterion we've had in place for more than 10 years, but we didn't publish it because anytime you publish criterion, you also give potential treaters the information of what they need to look for. Other groups have started to focus on a relatively low temperature heating, so they've published graphs like this. So unfortunately, now we start to encounter this less and less because treaters are paying attention. You have other bands. I mentioned before this 3161 series. This will be reduced as you elevate temperatures, and they will eventually transition into other structures like a 3060 series. Depending on the heating conditions and the chemistry of the stone, you may get more compound structures. But what is interesting or important with this is when you see these kinds of infrared spectra, you have the evidence that the stone has been heated, even at relatively lower temperatures. This is an effective tool. So now we're going to talk about relatively higher temperatures. This comes back to the question that Antoinette had asked. So really in the early to mid 1970s is when we started to see this transition to heating at relatively higher temperatures, so that threshold above what it takes to dissolve rutile silk. And this progressed continually through the 80s and the 90s, and today this is the most common form of heating natural rubies, is at relatively higher temperatures. Now to achieve this, people are using ovens. You can have simple ovens like this Lachmini gas furnace, more sophisticated like the Deltec electrical furnace, to very highly sophisticated like this Thermal Technologies electric furnace. And what they're doing here is they're controlling many variables when it comes to the heating process. So they can control the way they're ramping up the temperature, they can control the absolute, they can go to higher temperatures, so the absolute temperatures which they're reaching, how they're holding stones at temperature, as well as the ramping down of temperature. They may go through several cycles of this to get the results that they're trying to achieve. They can also better control the conditions of reducing conditions or oxidizing conditions. So that's all what this technology has really helped to advance the science of heating rubies and corundum and other gems quite dramatically. So again, here we're talking about dissolving above the threshold to dissolve rutile silk. Here's a ruby that has very fine inclusions of rutile silk. This is quite sparse. It's actually a pretty picture to see when you're looking at it with a loupe or with a microscope, but this is not the kind of stone which you're going to want to heat to dissolve the rutile silk. What you also can have happen are stones such as this. This is a piece of rough from Mogok, and here you see in the center part of the image a dense concentration or nest of rutile silk. And this is so densely concentrated that it's actually impacting the transparency of the stone. And so by heating this kind of stone at significantly higher temperatures or relatively higher temperatures, you're able to completely dissolve this rutile silk and thereby improve the transparency. So here's an example of a stone. This stone is actually in kind of the midway process of dissolving the rutile silk. You can see actually the threefold symmetry axis, which is still existing here. They're no longer needles, but stringers of particles. As you continue to heat this stone, as you heat it for a longer period of time or higher temperatures, you'll be able to draw all of this titanium. Rutile is titanium oxide. You're going to be able to pull all of this titanium back into the lattice so that the rutile completely disappears, significantly improving the transparency of stones. One caveat I also want to mention as we kind of go through these, not all needles and platelet type inclusions are rutile. Here's an example of hematite. This is an iron oxide. Iron diffuses much differently in corundum than titanium. This requires a much longer time period. John Emmett was describing geologic time scale you need for dissolving or diffusing iron. So as a result, even heating at relatively higher temperatures, you're not going to be impacting needles and platelets of minerals such iron oxide minerals such as hematite. So what do you start to see when you're heating also at relatively higher temperatures? You're seeing inclusions which are much more readily recognized as being altered by heat. So these were calcite inclusions. And so you see they've gone through thermal shock, they're translucent, they're white, they're heavily fractured. There's clear evidence. Again, you see this, you're able to make a definitive statement that a stone has been heated. Most minerals at the relatively higher temperatures are going to start to alter. Here's another couple of examples. We in laboratories, we as gemologists, we always like to know the identity of the mineral that we're kind of talking about, but inclusion scenes like you see here, both of these provide clear evidence that a stone has been heated, even though we're not able to recognize what the mineral originally was. The mere fact that you see these shows that the stone is heated, proves that the stone is heated. In fact, if you look at the inclusion on the left, this stone has actually gone under more extreme heating conditions. I'll talk about that a little bit later. So you're even going to want to start to ask yourself other questions when you see inclusion features which are so heavily altered as something like this.
Chris?
Yes.
I have a question here again.
Mm-hmm.
Let me read that for you. This is coming from David Graham, and he's asking, won't heating rubies with titanium create blue zoning? This is actually a very good question to explain a few things within.
Oh, okay. So yes, this is when it comes to what you want to do. So when you're heating under reducing conditions, you are also wanting to dissolve inclusions of rutile because you're wanting to facilitate the pairing of iron and titanium. So you're diffusing hydrogen in to help facilitate that process of creating this intervalence charge transfer. When you're heating rubies, you're heating under oxidizing conditions. So pure O2 kind of conditions you're going to be heating, because here you want to break this charge transfer. So you want to remove the heating. So this is why furnaces like what I had shown, they're very effective. They significantly changed what can be accomplished when you're heating corundum, because you can alter or modify between oxidizing conditions and reducing conditions. So I hope that answers the question that the gentleman had. So here's another practical kind of thing that I wanted to show people. When you're looking at a stone for whether it's heated and things, don't forget to look at the surface. You can use reflected light, because sometimes the inclusions, even sometimes spectroscopic data, may not give you enough information. But there may be areas, whether it's cavities or areas on the surface which they forgot to repolish after the treatment process, that show evidence of heating. They might have a melted or slightly molten appearance. You might have little droplets of contamination from the bricks of the oven as they kind of degrade. They'll adhere themselves to the surface of the stone. And so there are little practical things that you can look for here as well to help recognize whether a stone has been heated or not. So next I'm going to talk about the next phase of what we saw in the heating. And this is something which really started to take place in the 80s. It started to gain much more widespread usage in the 1990s. And this was heating rubies in particular with fluxing agents. And so this is a flux assisted heating, which facilitates the healing of fissures. And so this healing of fissures, it actually serves a couple of purposes. It improves the transparency by reducing the visibility of the fissures. It also improves the stability of the stones somewhat. That's why they commonly heat them in the rough, because trying to fashion them in the rough state, stones may not always survive the cutting and the polishing process. So they heat them with the fluxing agents to help really bond the material together. And so this is the next part that we're going to talk about. This is just kind of a quick diagram to help describe how this process takes place. They'll coat the stones with this kind of slurry of fluxing agents before heating. And as they heat it, as the temperatures go up, this fluxing agents that will melt, they'll flow over the surface of the stone, they'll penetrate into fissures. And what they actually end up doing is they partially dissolve the contact with the corundum. So it actually draws alumina into the melt as you're raising the temperatures and as you're holding the temperatures. And then as you're ramping down the temperatures, what happens is you actually facilitate the regrowth of corundum. So it starts to form as you're ramping down the temperatures. And so what's taking place now along these previously open fissures is you have a combination of characteristics. You have actually thin seams of regrown corundum. In the strict sense, it's a synthetic. You have remnants of this undigested flux melt. It's a vitreous melt. It's in the strict sense a glass. And you have small contraction bubbles. And it's these combination of things which actually are what reside along these previously open fissures. And several years ago, the labs kind of got together and we collectively decided to describe this material as heating residues. And so this is what we mean when you see a laboratory report that talks about heating residues in a stone, and then we quantify how much of this healing has taken place, how much of this heating residues is present in a particular stone. But this is the process that we're talking about. It was quite ingenious for the person who discovered it, and it's very widely used today. This is the appearance, typical kind of appearance of the induced healing of fissures through the use of fluxing agents. Most of you are probably familiar with this. A few years ago, when I was talking to a group about the flux-assisted heating and healing of rubies, one of the gemology students kind of had an astute question about the similarity in appearance to the actual flux fingerprints in a synthetic ruby. And this is true. They can sometimes have a very similar appearance to what you may see from a flux fingerprint in a Chatham ruby or a Kashan ruby or Duros ruby, these kinds of things. So you want to be sure to also look for other, when you have features such as this, you want to be sure to also look at the stone and try to make sure you're recognizing other naturally occurring inclusions, because I'm not talking about synthetics here, but you also want to obviously also be aware that you may have a synthetic in front of you as well. So now, up till now, we've been talking all about this healing of fissures and heating residues. This is, again, the healing of very fine fissures where the opening is very fine. Next, I want to talk about the infilling. And so infilling, this fluxing agents also have the ability to fill in areas on the surface. This can be cavities, which are present at the surface. These can also be broad fractures, where you have very little healing take place, and essentially what you have is just the fluxing agents or the vitreous melt infilling these materials. And so I want to show you a little bit of what that looks like. This is a broad fracture which has infilling. So this is really just kind of a sheet of heating of this vitreous melt that you have, a glass that's extending throughout the stone. Very little healing has taken place. When it comes to the filling of cavities, the best way to recognize this is through an overhead light source. The luster difference makes it very easy to recognize. On the left, you see a cavity which is fully filled, completely filled. The image on the right shows that sometimes these cavities are only partially filled. This filling of cavities is not always an intentional. It can be intentional to mask the presence of cavities, or it may be unintentional. Just a byproduct of not recutting the stone enough to remove all of these surface characteristics. So you can have complete filling or only partial filling. So next, I want to talk about, now we're even going to another level, which are more extreme heating conditions. Because under more extreme heating conditions, you're able to accomplish, again, even more. Here, you're able to start introducing other foreign elements in addition to hydrogen, which we talked about briefly. But you can look at elements like beryllium as an example. And so most people are familiar with beryllium diffusion. When you see this image here, this is from an article that John Emmett published. You see that's yellow sapphires and paparacha sapphires in particular are the ones that we most commonly saw or really drew our attention to begin with. But what John has demonstrated is that actually any color in corundum can be achieved after beryllium diffusion. This depends on many factors. This will depend on the heating conditions that were used on the stone. This will depend on the inherent chemistry of the stone, as well as how much beryllium has been introduced. But you have literally any color of corundum can result at the end of this. But today we're talking about beryllium diffused rubies. And so I want to compare it to the titanium diffusion, which we started to see in the 1980s. For those of you who are familiar with the titanium diffusion, this is a shallow penetration. So one of the best and easiest ways to recognize this is by putting the stone in immersion over a diffused light source. And you'll see a patchwork of coloration that's following the faceting. Beryllium diffusion, which began, as I indicate here, around 2000, is a different scenario because you're actually able to diffuse beryllium much deeper into the stone. And so you can even diffuse beryllium throughout the stone. So when you put a beryllium diffused ruby into immersion and over a diffused light source, what you want to be looking for is something like what you see here, which is actually a ring of yellow to orange color, which is also surface conformal. It's following the outline of the stone, but it's not a patchwork. It's more a ring of color. Some of the inclusion features that you may encounter, one of the sources that they commonly treat with for beryllium diffusion is a deposit known as Songea in Tanzania. This source commonly has crystals of rutile, so titanium oxide. After heating for beryllium diffusion, you see that there are actually halos of blue color which will surround these kinds of stones. Now, I'm not someone who ever speaks in terms of absolutes when it comes to criterion, but certainly if you see an image like this inside a stone, it should, kind of draw a red flag, and you're going to want to investigate it, whether to send it to a laboratory or look a little bit more closely for some other features to determine whether or not it's been diffusion treated. I also want to take a moment just to talk about chromium diffusion. This is something that did make its appearance for a very limited time back in the 90s. Then we kind of didn't see it because it's very difficult to diffuse chromium into corundum. Actually, it's a very shallow penetration. The colors are readily polished away when you're having to repolish the stone. However, not too long ago, we had a couple of stones come into the laboratory, which is just a reminder that it's best to always still be aware and on guard to look for stones that may come, old treatments that resurface. Our industry is constantly recycling the material which is there. So it's material that we haven't seen for a long time always has the ability to come back again. Now, these two stones happen to be pink sapphires, as a pink color as you see here, but in immersion you see that patchwork of coloration as I was describing for the titanium diffusion readily helps to identify these types of stones. So it's just a reminder to stay aware, stay diligent for all types of treatments. So next I'm going to end with this topic on composite ruby, which is a composite of natural corundum or ruby and a high lead content glass. Here we're going to spend a little time talking about this because this is actually, if you think about it in terms of just pure volume, this is probably the most abundant ruby material which you have available in the marketplace today. You don't have size restrictions. You can have any size you want. I've seen stones over 100 carats. You can match, you can have any number of stones. You go into the trade shows, you'll see volumes and volumes of this material. So I want to take a little bit of time to kind of talk about this material. The starting material is this very low-grade corundum, which previously had no use in our industry. It was mainly used for the industrial purposes as an abrasive. You can see this kind of material here, different colors of this material. It's a multi-step process. The first step of this treatment process is to actually, it's an acid treatment to kind of leach out and clean up the structure, to remove all of these foreign mineralizations and to open up the structure. And then in that state, the stones are not actually stable any longer. They're quite, you can even break them apart a little bit, some of them by hand. They're treated in mass then in a high lead content glass. You can kind of see here. Generally, these stones are single pieces, so a single piece of rough will produce a single cut stone. However, we do also encounter, because they're treated in such mass and you just get masses of this kind of corundum and high lead content glass at the end of it, they'll quickly polish and fashion stones, and sometimes you actually have discontinuous pieces of corundum which are actually held together by the head content glass. Sometimes you have more glass than ruby, sometimes you have more ruby and glass, but it's always an essential component, both of these things. Some of the things that you can look for, a bluish flash effect, these give a kind of hazy appearance to the stones. This you can see readily with a loupe. You don't need a microscope for this. Even by eye, if you've seen enough of these, you can start to already visually recognize there's something in the transparency, which is just a little bit different in the color and the transparency of these stones. But this is these are all fissures, so you get this blue flash effect throughout the stone. You'll see gas bubbles. Now you have to keep in mind, when you see a nice spherical gas bubble, this is a contraction bubble actually, it's occurring in a much larger volume of this high lead content glass. If you look at the large spherical contraction bubble in the center of this image, you're going to see an orange coloration around here. This is all one big pool of glass inside the stone. And so all of these nice spherical contraction bubbles that you see, they're all part of a much larger pool of glass, which high lead content glass, which is occurring in these stones. Now, when they're occurring more on fractures, so they've got boundaries of corundum, these contraction bubbles get flattened. So you'll see flattened contraction bubbles. All of these, everything you see in here, these are all flattened contraction bubbles. But again, representing areas where it's a larger volume of high lead content glass. You have cavity fillings are very, very common. This image actually demonstrates for me how impressive this treatment can be at times. This glass is so efficient and so effective. In the left-hand image, this was hard to actually capture because the RI match of the lead glass and the corundum is virtually identical. There's no luster difference you see here. What helped me to recognize it was the fact that the glass is softer than the corundum. So you have polishing lines which are coming in, but all of this, so these are the polishing lines, and this is all one large, this is the boundary of where the cavity is and where all this interior is a high lead content glass. Now, when I took off the overhead light and I just used the dark field illumination, that's what you see on the right. This cavity virtually disappears. You don't even see it. And so this, again, it just goes to demonstrate how effective and how efficient this treatment is. It's quite impressive, actually, on that standpoint. So next I want to talk about, this leads to the discussion of the extent of the treatment, because this is a statement which I make all the time, that literally all of these stones are much more heavily treated than they appear in the first period, even with close inspection. This was a stone which I had gotten, and I thought that this was, relatively speaking, this didn't seem to be that heavily treated with this high lead content glass. So I decided to do an experiment. I cut the stone in half and I etched the surface of the right half of the stone. And this surprised me because what happened, you see the whole surface is traversed by these different, by fissures. The difference is these are very fine fissures. So these are even more difficult to detect. The inclusion features that I was showing you, the flash effect, the gas bubbles, these are when you have larger volumes of this glass and very, very fine fissures. It's much more difficult to recognize this. And so this just is a clear demonstration that all of these stones, regardless of how much you think might be, they're all more heavily treated than you realize. This is why, for me personally, it doesn't make sense to make a graduated scale on trying to identify these pieces. All of these situations occur with each and every piece. And when it comes to the extent of the treatment, you're going to even have laboratory experts who are going to be debating what is the extent or the context of the treatment. And so it doesn't really make sense, in my view, to create a graduated scale for this product. There's also durability issues related to this. We've seen stones coming into the laboratory which have been damaged by a jewelry repair. When I was involved in an original study, we even found that some household products will damage and etch this glass. So this is an example of a stone where that has taken place. All this white that you see kind of around here, this is the etched glass. The reddish areas in between, that's the corundum. When we look a little bit higher, we can see these ribbons, these reflective ribbons, just show that the alteration and the removal of the glass, the etching of the glass, is only taking place to a very shallow penetration. These are fractures which are extending all the way through. So even with as bad as this stone looks now, the way it's been damaged, this still only part of the glass has been removed. And so this also led to another level of treatment, or another extent of the research that we did, and that was trying to remove all of the glass. And in worst case scenarios, this is what we found. The structural integrity of the ruby was not even able to remain intact as a result of the process of removing all of this. When I sent this to someone to help me remove all of the glass, they sent me back literally powder, grains of corundum. They felt terrible. They thought they ruined something. And I said, no, this is a little bit what I expected to find. So not all stones, not all composite rubies will end up like this when you remove all of the glass, but there's a significant number of them that do. And so I want to talk just a moment about why a name? Why did I come up with this name, composite ruby, for this material? I was actually criticized for it when I came up with it several years ago. I decided that it was important to take a very strong position on this material. It was a different product. This is not like your more commercially heated stones that we were talking about just previously. And there are two essential components to this material. That's hence a composite. You have natural corundum or ruby, and you have a high lead content glass. If you remove either one of these two components, you do not have this product. And so it really is a composite of these two materials. And in the same vein, it allows for these stones to be clearly distinguished from the more commercially heated rubies that we've talked about before. It identifies that these stones, they're not synthetic. It establishes that it's not an imitation. There is ruby in this product. And when used at all levels of the supply chain, it eliminates the potential for any gray area which could allow for misrepresentation to take place. And this is a very important aspect. Early on, you had trade organizations such as the AGTA and the GILC. They embraced the use of this term composite. Today, they also recognize things such as a hybrid or a manufactured product, but composite was really the leader in kind of establishing this material as a separate and distinct product. More recently, you have CIBJO. So CIBJO did an important ruling on their 2013 at their Congress, where they actually changed the definition of the term composite to allow for this material to be categorized as composite ruby. Under the new FTC guidelines, you see that they're endorsing the use of the composite, manufacturer, or hybrid product, but also with special disclosure about the special care requirements. Now, here's another question that I've gotten many times over the years, and why not just call it glass filled? I even had one of the GEM-A instructors kind of email me this question a while ago. And they wanted to know, because there was confusion. I guess it was being taught a little bit as a glass filled, these materials were glass filled. And so I started with a couple of important aspects. One, I want to just show a little bit of the pricing structure in this. In a composite ruby, like you see on the side, you're talking plus minus $10 a carat. You'll see material for $2 a carat, or even less. The most expensive I've seen it is probably $100 or $120 a carat. Whereas the heated Mongsu rubies, for example, with flux-assisted healing of fissures, this is a different price point. This, I actually asked the steward this morning to give me a price, 2-3 carat size, nice quality like this. What's the price? He said about $3,000 to $4,000 a carat. Now, I've seen heated Mongsu rubies with heating residues go for upwards to $20,000 or even $30,000 a carat for very high quality stones. But you can see this is a much, much different product which is there. And if we go back in time, Antoinette and others who have been in the industry a little bit longer, you're going to remember that especially during the 90s, in the late 80s and the early 90s, when this flux-assisted healing of rubies was taking place, these stones, because the flux melt produces a vitreous melt at the end, it's technically a glass, these stones were referred to as glass filled. And so the industry already has a kind of familiarity with this term, glass filled, for stones such as a Mongsu ruby or a Mogok ruby or a Kenyan ruby that have been heated but flux-assisted healing of fissures. So that term is already familiar for many people in the industry. And so when they hear this material also being called glass filled, they start to, there's easy for there to be confusion between these two products. And I think it's very important that we do not allow for any potential to have these stones kind of be confused with one another. When we talk about the guidelines for disclosure, I just show quickly the FTC, Federal Trade Commission guidelines in the US. If a treatment is not permanent, if a treatment leads to special care requirements, or if a treatment has a significant impact on the stone's value, any one of these requires special disclosure, that a treatment be disclosed. Obviously, for composite ruby, all three of these apply. And one of the other things I want to mention, if I just go back to this image of these two stones, you know, unheated rubies, heated rubies, this is the main part of the market for rubies around the world today. And we want to be sure that also when we're looking at policies as an industry, as a laboratories, we want to be cognizant and just prudent to make disclosure that helps to protect certain products. Now, if it was the exact same product, I would have no problem kind of disclosing it the same way or describing it in a similar way. But the care requirements are much different for these two. The fact that a significant portion of the stone consists of lead glass, and the fact that there's a very significant value differentiation between this really just helps drive home the point that this material should be handled clearly separately from this more commercially heated stones. So
Hi,
what's
Chris.
yes, sorry. Are we out of time?
I have questions regarding the glass-filled material. So before you move on, I just wanted to ask you those, and then
Yes.
the very first short one from Lucy Cook. She's asking, can glass-filled rubies be worth more than 1 to 5 per carat?
Well, again, when you say the term glass-filled, are you talking about a composite ruby, or are you talking about
it is composite, yes.
Yeah. So composite ruby, I mean, it's basically what, if you go to the trade shows, you'll see, you know, material which is $1, $2, $5, $10 a carat, kind of just in bulk. One of the things to kind of remember that I haven't brought up before is also the kind of idea of resale value. Remember, I kind of talked about how material always comes back into the marketplace. And if you have obviously an unheated ruby retains value, grows in value over time, this material only becomes rarer and rarer. But even the material which is heated, like a Mongsu material, Mogok material, other sources, that's been heated with fluxing agents. This material also has a certain market value coming back into the when they come back into the market. If you were to take a composite ruby and bring this back into the market, it virtually has no value. So this is also another kind of consideration. Obviously, as a lab, we don't get involved with the valuations, but it is something that we should at least be cognizant of when it comes to disclosure.
From my experience, there are composite rubies sold up to $200, $250 per carat in wholesale market if it is large and clear. So there are actually grades for it. So that's something. I had another question from Antoinette, but I believe she took it away. I can't read that anymore. And I will have other questions on flux-sealed rubies and heat treatment. So I will get back to those after your talk is over. I just wanted to ask those glass-filled ones first. Okay.
Yeah. So again, just from my standpoint, for the woman who asked the question, I wouldn't suggest using the term glass-filled, because again, it's not quite sure which material you're talking about. When you use the term composite ruby, it's very clear you're talking about this lead glass treated material. And so when it talks about what's the harm, again, especially as the industry is kind of coming out of the current situation around the world, we want to be sure that we're all acting responsibly, and we don't want to do things which could harm the reputation of our industry. These were kind of exposés which were in MSNBC as well as in Good Morning America, where at the time that this came out, these were quite highly publicized because you had retail establishments and some people in the trade who were not properly disclosing this material. And so this is the kind of thing we want to be careful to make sure that as an industry, we're doing the responsible thing. We're protecting consumers, we're protecting the marketplace, because without consumers, there is no marketplace.
Chris, speaking of composite again, before you move on, I have Antoinette asking this question. I'm reading that to you. Lead glass filled ruby, since lead glass weighs so much more than ruby, to what extent is the carat weight also impacted in a heavily filled stone of this type? Also, how often do you find antique pieces with rubies having their original cuts and possibly even showing wear that have been heated subsequent to their period to improve color?
Yeah, these are things that we see. So when it comes to the first question about how much weight is the lead glass adding? So how much are you actually paying when you buy a stone like that? How much are you paying for lead glass, and how much are you paying for the ruby itself? This is variable, depends on the stone, it depends on the extent of the treatment. I never wanted to get into the topic of trying to quantify this treatment. When you're talking at values this low, typically the cost of a laboratory report is more than the cost of the stone itself. So again, for me, it doesn't really make sense. You mentioned stones that maybe as high as $200 a carat or even $250 a carat. I've not seen that personally, but I would say, okay, if that's been seen out there, it's still significantly lower than a similar appearing ruby, even a ruby that's heated with flux-assisted healing. So if you have similar quality looking at each other, larger, very transparent, that flux-assisted heating of a ruby, that stone is going to have a much, much higher valuation than $200 or $250 a carat.
Thank you.
So I think that it's, the topic of how much weight is there, this is academic, but each stone is going to be different. But always the lead content glass does compose a significant portion of the stone by the vast majority. And also when you have to think about it as a laboratory, when you think about disclosure policies, you kind of look at it like a Gaussian curve. When you establish a policy for how to disclose, you don't want to establish a policy for the exceptions. You establish policies for the rule, and then you allow flexibility for the exceptions. And so the rule of this material is by far what I had shown. Stones that are very heavily treated, where the glass is a very significant portion of the stone. Could you have a very small percentage of the material that's produced which is not as heavily treated? Yes, but that's the exception. And when you're creating disclosure policies and you're just reporting policies, you want to try and handle the rule as far as instead of the exception. Now, when it comes to treatments, we've seen this both with composite ruby as well as the more modern type of heating, where people will remove an older stone from an antique piece and put in a composite. We've had this happen. This for me is, I actually hate to see this, because when you see an antique piece of jewelry with a ruby in it, people obviously they're going to think, okay, they want to be sure it's not an early melt-grown synthetic, but they're thinking, there's a good chance there were only a few sources producing, an antiquity. So you're talking, there's a good chance it could be Burma. There's a good chance it's going to be unheated. And here, what they end up buying is an antique piece of jewelry with a composite ruby in it. This is, really an unfortunate practice that I see happen. But we also see this with more traditional heating or more commercial heating, where they've taken out the stone and either improved the stone that was in it or simply exchanged the stone.
Okay. One more question related to the composite material. Do the flux, this is coming from Audley Edgedorn, and she's asking, do the flux healed rubies also show blue flash like the composite material?
So in general, no. When you have, you're involved with healing process typically with these heating residues. So they're going to have the appearance that I showed before, where you have kind of communication tubules, you have negative crystals and so on, and transparent areas in between, which is the regrown corundum. And so you don't typically have that. But with that being said, I do want to say there is there's a small number of stones which I've seen over the years, heated Mongsu stones, where the fluxing agent actually had a bluish cast to it, but it's a completely different appearance than this kind of wispy kind of flash effect that you see in the composite ruby.
Thank you.
Okay, so kind of concluding with this presentation. So again, here we have the fundamental questions when rubies these are the three fundamental questions that you're going to want to ask yourself when rubies kind of come across your desk or into your place of business. You're going to want to ask, kind of, is it unheated? Is it heated? Is it composite? And just from the position of a laboratory, it's not the laboratory's position to say what's good or what's bad. So all of these products have their place in the market. But for you going forwards, these products are going to be right or wrong for a particular entity or a particular individual for various reasons. And so it's for each one to make that decision of whether this is the right product that they want or not. But you have to be aware of what to kind of look for. So in the beginning, let's say you've looked at the stone and you've determined that it's unheated, in your opinion, you want to be sure to check for additional enhancements, things like oiling. Oiling could be colored as well. I didn't talk about colored oil, which can help improve a ruby. I didn't talk about things like coatings because we don't find too many coated stones that are represented as rubies, but it has happened in the past. So you're going to want to look for things like additional enhancements. If you determine that it's heated, these are some of the questions you want to look at in a little bit more detail. Is it a relatively low temperature heating? Is it a stone that was heat alone? So there's nothing else done to it, just heat, relatively higher temperatures? Or was it heated with the use of fluxing agents? So are there heating residues? If so, what's the kind of quantification of the heating residues? And then of course, has there been something like beryllium diffusion, which has taken place? And if you determine that it's a composite, just be aware that if you're going to sell this on, you also need to communicate special care requirements. And so this next slide, I'm going to end with something that's a little bit forward thinking. This is what I expect to see in the next step of ruby heating. We've seen now, this is obviously a blue sapphire, and we're seeing sapphires that are heated under pressure. And I really think this is the next evolution of what we're going to see with ruby treatments. We haven't encountered it just yet, but it's just a matter of time before they perfect the regiment and the routine, which will help rubies. And so I think really this is what I expect to see next in terms of ruby treatments. So I want to thank you all for your time and your attention. I really appreciate it. Again, this was my first time doing a webinar, so I hope I did okay. I also want to make a special notice. I want to thank Cheatham for finding the most recent photograph of me that she could when she sent out this news, because we all know how these webcams can, distort the appearance, make someone look older, give them gray hair, less hair, maybe even facial hair. But she really took the time to find the most recent and show how young and charming and looking I still am.
You have more hair now. I told you not to pick on me on that.
So thank you, everyone.
I'm
happy to answer any questions.
Sorry. Yeah, I have a few. I actually wanted to ask you the question, and then two questions came back to back related to that. So let me read those questions first, so maybe we can start the discussion. First one came from Shirley Mitchell asking, are the blue spots found in all colors of sapphire and ruby? This came right at the diffusion treatment portion of it. And then right after that, Stuart Robertson is asking, are there any instances of titanium pooling type inclusion seen in unheated magmatic material? So I think we need to explain a little bit more about the titanium rich inclusions versus diffusion and an extreme heat situation altogether.
Okay, so just read me Shirley's question again. So
Shirley says, are the blue spots found in all colors of sapphire and ruby?
Okay, so when this is when we're talking about inclusions of rutile which are pre-existing inside the stone.
Right.
As you go above this threshold to start dissolving the rutile inclusion, you're actually dissolving titanium back into the lattice where it has the opportunity to pair up with iron. And so when you're heating under oxidizing conditions, typically this pairing is not taking place. Titanium is entering the lattice, but it's not creating this intervalence charge transfer. That being said, there are times when I have encountered rubies. I had an image which, in order to shorten the presentation, where you saw this spotty blue, the typical kind of spotty blue coloration that you see in a heated blue sapphire was actually occurring in a ruby. And so this is something you don't commonly see. I've seen it on rare occasions happen in a yellow sapphire or in a podporacha even colored sapphire. But typically those kinds of colors, rubies, yellow, orange, podporacha type colors, pink sapphires, these are heated under oxidizing conditions. So it's not as common that you will see the titanium, which is pulled back into the lattice, create this intervalence charge transfer with the iron. You may see it, and if you do, it's a good indication of that heating has taken place, but it's the rarity more than the norm.
Can I add something to that? I normally explain that you have to have extreme heat conditions. It really needs to be emphasized, and then the titanium rich inclusion in order to create that blue pooling. It doesn't matter what the host material's color is, right? Would that be a simpler statement?
Yeah, I mean, it's the host color is obviously dependent on the inherent chemical composition.
Right.
And whenever you have these chromophores which are interacting, it's always kind of a consideration of the overall chemistry which is present in the vicinity. But in general, I would agree with what you're saying. You
Okay.
certainly want to be above that threshold and so forth.
Thank you. I have another question coming from Lucy Cook. Can you please elaborate on the last slide? Could you go back to that?
I also wanted to answer Stuart's question. I'm sorry.
Oh, yeah, sorry. Let me read that back to you. Where are you? Here. Are there any instances of titanium pooling type inclusions seen in unheated magmatic material?
I'm not sure I understand the question. Do you know exactly what he was referring to?
Like the magmatic material, we see all sorts of inclusions look like heated, but it is actually heating naturally occurred. And when they are sold as unheated, obviously they are not treated in a lab or in a factory. So he's asking, could we see the same blue coloration or blue pooling in this material too?
You don't typically see these kind of halos of blue color from that, but it's a very good point. You have magmatic deposits or magmatic related deposits around the world. And for rubies, here we're talking about, for example, the rubies from Thailand, the rubies from Cambodia, the rubies from Lake Baringo in Kenya. These are all from basaltic deposits. And so this required an eruptive event to bring them to the surface. And so they experienced a certain amount of natural heating just being brought to the surface. So what we're trying to do is we're trying to ascertain or determine whether heating that we're seeing has occurred after the stones reached the surface, because inherent inclusion features are showing certain kind of conditions or features that we associate with the production of heating. In these instances, it just happened to be a natural annealing which kind of took place. So rubies and sapphires from magmatic deposits, they represent an additional challenge simply because of their kind of formation and how they're brought to the surface. So it is a good point for Stuart to bring up. I had also removed that from the presentation to shorten it a little bit. But these halos of blue color, this is not something that I've seen naturally occurring.
Thank you. Can we go back to Lucy Cook's question? Can you please elaborate on the last slide?
The last slide, does she mean this one?
I believe so. Let me check if she replied. Lucy, if you could reply yes or no, then we will know.
Because if we talk about this one, this is something
yes,
that's
it is. Yes, this one.
So
thank you.
There's a relatively new product that's come into the marketplace, which are blue sapphires that have been heated with pressure. So you can see they're using a diamond press kind of apparatus, and you see they use about a gigapixel, which is about 10 kilobars of pressure, and they heat for about 5 minutes. And this has been shown to be a very effective tool at heating blue sapphires. It only takes about 5 minutes to heat them, so it's a very rapid process. Some laboratories disclose it as just together with the more commercial heating. Labs such as ourselves and GRS, we've taken a more conservative approach in the beginning, where when we can detect that a stone is heated with pressure, we disclose it. And it's because, from my standpoint, we're still at the early threshold of this. So we don't know really what's going to come afterwards. And so I prefer to take a little bit more conservative approach on disclosure of this material. But it is there. It's a group in Sri Lanka which is doing it. They've actually been very responsible in informing the trade, educating gemological laboratories, giving gemologists the ability to come and look at their process and their procedure. So I give them full credit for transparency on bringing this product to market. It's just something that, again, it's a little forward thinking. Right now, what they're working with exclusively is blue sapphires. But it's just a matter of time whether this group or another group figures out really the proper type of regimen they need to help improve rubies in the same way. Thank you very much, everyone. Take care, be well, stay safe.